Hey everybody, welcome. When isotopes are unstable, they can undergo a fascinating process known as nuclear decay. In this video, we're going to focus on one of the major types in which unstable isotopes decay in order to become more stable. That process is known as beta decay. We're going to look at it conceptually, break it down in easy and understandable format, and then of course, we're going to focus our attention on how to answer questions involving writing nuclear equations to describe this process. Thank you for joining me. I can't wait to teach you about this topic. I hope you're ready to learn.
What's up, everybody? Welcome to Neil's not so boring world of chemistry. Let's go into the lab and take a deeper look.
Okay, so as you guys know, because you're in a high school chemistry class studying nuclear decay, or maybe you've watched my other videos on this topic, right? You've watched them and liked them. Okay, but you're aware of the fact that nuclear instability tends to happen because of an imbalance in the proton to neutron ratio. Now, there isn't one set ratio that always makes atoms stable, but we know that it's those two particles in the nucleus and the way that they interact with each other that's going to cause an atom to be radioactive. So the question is, what can an atom do if it's got a problem in its nucleus that's causing instability, namely too many neutrons? Well, this is where beta decay is a super useful decay process. Here's what happens. One of the neutrons can be converted into a proton and an electron. That's right, it can actually, you can think of it as transforming or splitting from a neutral particle into two charged particles. Now, this always made sense to me as a concept because I thought to myself, well, if I was to combine a positively charged particle and a negatively charged particle, and I sort of crush those two things together, I imagine the charges would cancel out and I'd get some kind of neutral particle, like a neutron. But in beta decay, we see the opposite happening. The neutral particle is splitting up into the two charged particles. Now, how does this all work? Well, as you might imagine, it's pretty complicated physics. And as a high school chemistry student, all you're going to be asked to remember is the weak nuclear force is responsible. That's right, this is a force that only operates within the nucleus of atoms, and its main function is taking neutrons and converting them into protons and electrons. And you really don't have to know anything else about it beyond that. So now we need to answer a question. What's this nucleus going to be like after the beta decay event has happened? Once one of the neutrons has been converted into a proton and electron, where do these particles go? Does the nucleus now have an electron hanging out in there? Let's find out. So to understand the repercussions of a beta decay event, let's take a look at the nucleus of a beryllium-10 atom. On the board here, that's what I've modeled for you, and we're going to imagine that one of these neutrons is throwing off the stability of the nucleus, and the weak nuclear force is going to convert it into a proton and an electron. So we're going to remove one neutron that was causing the instability, and we're going to replace that with a proton and an electron. Now, it turns out that the proton, this new proton, stays in the nucleus of the atom. And the electron that was created actually leaves. This is jettisoned or exited from the nucleus. It flies out like a small fragment or bullet. And this is actually known as a beta particle. Now, of course, you might be saying to yourself, well, isn't it just an electron? I mean, yeah, technically it is, but because it's not like most electrons, which are just hanging out in the electron cloud, and because this electron came from the nucleus and is now going to leave the atom entirely, we give it the name beta particle. Now let's go back to that proton. This is an extra proton that wasn't there before. So what does this mean for the identity of the atom? Well, the atomic number is no longer going to be 4. Now it's going to be 5. And we know from understanding the basics of chemistry that when you change the atomic number, you change the element's identity. So I'm going to have to now switch this from being a beryllium atom to, that's right, a boron atom, element B. So in the beta decay process, we have an electron that's going to be shot out. We call it a beta particle. And we have a new proton, which changes the atomic number and the identity of the element. It's also worth noting that the mass number doesn't change. Why is that? Well, we did lose a neutron, so that would have dropped the mass number down by 1, but we gained a proton, which would raise it back up, so the mass number remains at 10. We have the atomic number increasing by 1, a new element, and a particle, a form of radiation, which is going to be leaving the atom. So one skill associated with beta decay and all of the nuclear decay processes that you're going to be asked to learn is writing nuclear equations. And I want to conclude the video segment with an example of how to do that before we get to some practice problems that you can try. Behind me is the nuclear equation for the beta decay process we just described. That was the beta decay of beryllium-10. So let's break it down and figure out how we can consistently write great beta decay equations. So first off, we're going to start with the element that's radioactive. In this case, it was beryllium-10, atomic number of 4. Then, of course, we use the arrow to document the change that's about to occur. Now, in this process, we're always going to have two products. Firstly, we're going to have the new element that is formed. Now remember, we said that new element is formed because we get that extra proton that joins the nucleus, and that's going to increase the atomic number by 1. So we're always going to see in beta decay equations the atomic number going up by 1. In this case, it's from 4 to 5. We also described why we expect the mass number to stay exactly the same. We are losing a neutron, but we're gaining a proton, so overall they're the same number of particles. So you'll notice that the mass number stays at 10. Now, of course, when we increase the atomic number, we have to remember to look up this new atomic number on the periodic table. You never want to have the same chemical symbol on either side of a beta decay equation. Okay, lastly, we have to document what happened to that electron. Remember, we're calling it a beta particle. And in order to do that, we draw this symbol here. This is telling me that when this atom decayed, it formed two things: a new atom as well as this extra electron that was shot out of the nucleus. And we use this symbol to describe that electron. Now, in certain textbooks, certain teachers' classrooms, certain videos, you may see the beta particle described using this symbol. And this is the Greek character beta. I tend to just use the electron symbol using that lowercase e, but this and this are equivalent. They mean the same thing. Now, here's where it can often be confusing, is understanding why this -1 is down there. Why is there a -1? And that's because in all nuclear equations, you want to make sure that the number of particles on one side of the equation equal the number of particles on the other side of the equation, right? So on the left side of the arrow here, I have 10 particles in my mass number and 4 particles in my atomic number. And that means, according to the law of conservation of matter, I have to account for 10 particles on this side of the equation and a total of 4 particles on that side of the equation. So the 10 is easy to understand because the mass number doesn't change. So we just put a 0 there because we don't want to change anything about the total number of particles in the mass number. The 0 keeps everything balanced. But why do we need this -1? Well, that's because if the atomic number went up by 1, this -1 will cause the sum on this side to be 4. And that's going to be the same as the total number of atomic number particles on the left side. So that -1 is just there so that mathematically when you add these two numbers together, you get the same number that you started with because matter has to be conserved. It cannot change even in one of these nuclear process decay equations. Okay, now we're going to give you guys a chance to write an equation of your own and check for comprehension and understanding. So if you're ready, we can go over some of the major concepts covered in this video before we give you a chance to practice your beta decay equation writing skills. So let's start with what beta decay is. It's a nuclear process, and it's going to happen to a radioactive isotope in which the problem or root cause of its radioactivity is extra neutrons, and beta decay can lower the number of neutrons by 1. This process is controlled by one of the 4 fundamental forces in the universe known as the weak nuclear force. What are the results of beta decay? Well, you're going to lose a neutron. You're going to be adding a proton, and remember that means it will increase the atomic number and in turn create a different element. Lastly, we're going to see the discharge of something called a beta particle, and that's just an electron. Here's a tip. Remember that the mass number of an atom that undergoes beta decay doesn't change. Yes, it's true that a neutron has been lost, which you would think would lower the mass number by 1, but you've gained a proton, and so the total number of particles in the nucleus is exactly the same. Okay, here's your practice question. Pause the video and try to write the nuclear equation for the beta decay of lead-210. Continue watching for the solution. Okay, here's the correct nuclear equation. Now, you can see here on the left we're starting with the symbol that represents our radioactive nuclei. That's lead-210. The arrow signifies a change. Now, this is where we add our beta particle, or our electron, and you'll have to remember to put in this -1 on the bottom there, and that's critical because that -1 is going to allow us to create a new element that has a larger atomic number. So we have to ask ourselves, what number, when added to a -1, would equal the 82 on the left-hand side of the arrow? So of course, we're going to increase that number by 1 and go to 83. 83 minus 1 equals the 82 that we started with. Now, how did I get the rest of the symbol? Well, I knew that the 83rd element was bismuth because I looked it up on the periodic table, and you should do the same. Now, the mass number 210 is always going to be the same as the mass number that you started with. That's one of the features of beta decay. No change to the total number of particles in the nucleus. Okay, I hope you got this question right, and I hope if you have any further questions, you'll leave a comment for me. I want to thank you for watching this video and supporting the channel, and I look forward to seeing you in the next edition of Neil's Not So Boring World of Chemistry.